Hello, everybody, and welcome to our continuing discussion about coming up with confidence intervals for the mean of a normally distributed population and interpreting them. So, to this point, we have pretended that we knew sigma, that we somehow knew the population standard deviation, and we were trying to estimate mu. This is not a very practical thing. It just does not come up very often. But it was a simplified scenario that enabled us to see a few things without this added complication I'm about to introduce. The added complication is not that bad. It's just a little bit different, but it's a useful starting point to just leave it out for a little bit and say, hey, let's look at the scenario where sigma is known, but that's not what happens in the real world. So here we are, right? Getting to this case where sigma is unknown. And when the population standard deviation is unknown, we're going to estimate it with the sample standard deviation and proceed in a very similar fashion. But something fundamental happens that we're going to need to account for. So we had this notion. This is what we've been talking about so far. If we happen to know sigma, we came up with this. I showed you mathematically how this arose, and then we calculated for a simple example and talked about various aspects of it, that sort of idea. Now, it's going to be a bit of a change. Fundamental, this notion we talk about in sampling distributions. When sampling from a normally distributed population, x bar minus mu over sigma over the root of n has the standard normal distribution. That's just the case. We looked at that when we talked about sampling distributions. That was an important notion. And so we had sigma in here, and we used this when deriving our confidence interval for our population mean mu. And sigma could go in there. What if we don't know sigma? Well, we have nothing to put in the formula. Oh, wait though, sigma is the population standard deviation. Why don't we put the sample standard deviation in there? If we don't know sigma, let's put in the sample standard deviation. Good thought. Let's do that. Something fundamentally changes. Something fundamentally changes when we do that. We've got this quantity, and we are replacing this constant, sigma. It's a constant. It's some theoretical or value for your population, your standard deviation for your entire population, a number. We are replacing it with our sample standard deviation, which is a statistic that is a random variable that has a probability distribution and would change from a sample to sample. So the value of the sample standard deviation would be changing from sample to sample. And when we try to use it down there, which we can and will do, something happens. There's extra variability associated with that. And this quantity does not have the standard normal distribution. It has something we call the t-distribution. T-distribution with n minus 1 degrees of freedom. T-distribution with n minus 1 degrees of freedom. Well, we're going to look at the t-distribution in a moment. The t-distribution is going to have one parameter, the degrees of freedom, n minus 1 for the case we're looking at here, and I have more mathematical description of the t-distribution elsewhere if you're into that, but I'll fill you in on the broad strokes as needed for our applied statistics here. One thing to note, I'll just mention this right up top, our sample variance. Remember when we're doing our sample variance and we're just doing the sum of our xi minus x bar squared. So back in week 1 or 2, or whenever we did this, and we divided by this. And now we're saying this. Not a coincidence. Not a coincidence. Here we've got S. We're replacing our sigma with S. We're estimating sigma. We're putting S in here. Our sample variance had n minus 1 degrees of freedom, and our T is going to have n minus 1 degrees of freedom. Yes. Not a coincidence. Those go together. Your degrees of freedom for a T are going to be the degrees of freedom for whatever variance you are using. It's a little casually phrased, but that's the gist of it. So we're going to have different t-tests. There's all sorts of t-tests and t-methods, t-statistical methods, not just tests. We haven't talked about tests yet. There are such a thing as t-tests and methods based on the t-distribution, wide variety of settings. The degrees of freedom are going to change. But remember this notion. It's linked. It's linked because the standard deviations here and those degrees of freedom are tied in that way. Okay. What is the t-distribution? All right. Well, I have more mathematical description, as I said, in videos and text, but we're looking at the casual bit here. We're just going to get what's needed for us. We might imagine. Let's just sort of imagine for a moment, though, when we're doing this, that this standard deviation from the sample, when we put that in there, that's going to incorporate a little bit of added variability, right? Just going to have a little bit added variability because we're not putting a constant in anymore. We're putting in a statistic that's a random variable. There's a little bit more variability. But overall, it's going to look quite a bit like the standard normal distribution, isn't it? Yeah, it is. And then wait a minute, as your sample size gets really big and S gets to be a better and better estimator of sigma, let's say, isn't it going to get better and better and closer and closer, let's say, to the standard normal? Yeah, it is. So let's look at these things then. So with that notion in mind, here we go. So T has that one parameter, the degrees of freedom. So I've got a standard normal, which is the solid one here, right? And then two different T distributions. The degrees of freedom has to just be positive, but for our purposes, it's typically going to be a whole number, and often bigger than 2 and 4, but I chose these for visual reasons here. So we've got our standard normal distribution. Remember, our standard normal is symmetric. Our standard normal distribution is symmetric about 0, right? So we had this symmetric about 0, and it had the mean of 0, right? Mean 0, median 0, also, right? As well. And the variance was 1 for a standard normal distribution. That's the standard normal distribution, the curve we're familiar with, the black curve here. The T, it's a little different. A little different. It is symmetric about 0 still, though. Hey, wait, that's similar. Whatever the degrees of freedom, doesn't matter, still symmetric about 0. The mean is 0, okay? The mean is 0. There's a technical mathematical thing where your degrees of freedom have to be greater than 1 for that to happen. That's just technical mathematical stuff. Don't worry about it, right? Unless you're into the technical mathematical details, the mean is 0. We just got some mathy stuff at precisely 1 degree of freedom, but we're not going to be dealing with that situation. And the variance isn't 1, it's the degrees of freedom. So we typically have the degrees of freedom represented by nu. So nu are going to be our degrees of freedom. So T with 2 degrees of freedom, T with 4 degrees of freedom, and nu is the degrees of freedom. I'll just, I haven't written it up like that, but have the nu. So nu minus 2. And nu is the degrees of freedom, right? That's what I'm getting at here, just the degrees of freedom. So we get a symbol for the degrees of freedom. Nu over nu minus 2. But this has to be for nu bigger than 2. There's a mathematical thing there. Don't worry too much about that. Just don't worry too much about that. So let's look, though, a couple of things. Symmetric about 0 means 0. All right, that's pretty similar to the standard normal. Visually, what do we got? Visually, we have that the T distribution here has this lower peak, and more area in the tails. Or another way of looking at that is that greater variability, right? This degrees of freedom over the degrees of freedom minus 2. So let's say for 10 degrees of freedom, we're going to have 10 over 8, and it's going to be 1.25. And that's bigger than 1. So the T distribution is going to have a greater variability, greater variance. And the consequence of this, and when we're looking at this, or another way of thinking about it, a lower peak and more area in the tails. More area in the tails. Okay, but we might notice as we go from 2 to 4, right, 2 to 4, and compact notation, we might write this as a T on 2 degrees of freedom and a T on 4 degrees of freedom, right? So T, that's kind of an ugly 4. So in brackets, I might write it like this sometimes. Sometimes I'll leave it implied. Sometimes I'll say T with 2 degrees of freedom, just say it out like that. But this is sort of more compact notation that we'll see. What do we see as we go from 2 to 4? What do we see as we go from 2 to 4? This blue curve is getting closer to the black, closer to the standard normal. And this is exactly what's going to happen with the T distribution. Makes sense, I think, right? That larger and larger sample size, we're going to get closer and closer to the standard normal. And that's what happens mathematically. And if we think about this variance, let's say we had 1,000,000 degrees of freedom. Then the numerator's 1,000,000, the denominator's 1,000,000 minus 2, it's pretty damn near 1. And the variance is really close to that of the standard normal distribution. And the two curves are very, very, very close. And so fundamentally what's happening here, what happens mathematically, and it's an essential thing to know, that the t distribution tends toward the standard normal distribution as the degrees of freedom increase. As the degrees of freedom increase, the t's getting closer and closer to the standard normal. And in fact, in the mathematical limit, as we let those degrees of freedom shoot off to infinity, it becomes the standard normal distribution in the limit. So, t distribution, lower peak, heavier tails, more variability, comes closer and closer to the standard normal distribution as the degrees of freedom increase. I have videos on this where I have visuals of all of this in a little bit more detail. So you can watch those videos if you want some more visuals of how all this is happening, but this is the important stuff for us. And again, this t's are rising when we're using our sample standard deviation in the formula. All right, so this is what we got. Same formula, right? Essentially. So sampling from a normally distributed population, and we don't know sigma, so we can't use it in the formula. This is the same formula as for the sigma known case, except in the sigma known case, well, we put sigma in there, but we used z where t now is. We use z where t now is. S over root n is what we call the standard error of x bar. We learned that back in sampling distributions. That is our estimate of the standard deviation of x bar in repeated sampling. So the standard error of x bar is this thing, and that standard error is going to come up in a lot of different spots, different scenarios, and we'll have different formulas, but of a very similar structure involving the standard error. So what's this t? This t, it's the same deal as for the standard normal, except it's for a t now. Okay, just for a t now. And we're going to have n minus 1 degrees of freedom. So I don't always write in the degrees of freedom with a t. It's implied that it has to have degrees of freedom. There's an infinity of t distributions corresponding to all the different degrees of freedom. So then there's a generic t. But when I write t, I'm saying t for the appropriate degrees of freedom. And for us, right now in this problem, it's n minus 1 degrees of freedom. It's the exact same structure as for the case where we're using the standard normal distribution. It's just with a t distribution now, and we're going to get these values from R or other software. So it's the same deal, it's just a different distribution. So let's look at a basic one here. If n is 10, what is the appropriate t value for a 95% confidence interval from mu? Okay, when we're doing this, we have our t distribution with our 9 degrees of freedom, because of course our appropriate degrees of freedom are n minus 1, 10 minus 1, that's 9, right? We've got that. And we're going to draw out this picture. So when we're doing it by hand, we just sort of casually draw this out, right? And say zeros here, we do that kind of stuff, right? With a t distribution looks something like this. But I've got this plotted out here. I kind of squished this one. I'm going to go back and sort of But this is it. This is still a t distribution with 9 degrees of freedom. I just don't like I've squished it in a little bit too much on the scaling. But anyway, this is a t distribution with 9 degrees of freedom. And we want a 95% confidence interval, so we put 95% of the area in the middle. And then we split up the remaining 0.05 evenly into the two sides. 0.025 on one end, 0.025 on the other. And we find the t value that makes that happen. And so with 9 degrees of freedom, when we go to R and we find the value that has an area to the right of 0.025 or an area to the left of 0.975, we find that t.025, this 9 degrees of freedom, is to 3 decimal places 2.262. That's the appropriate value that we'd use in a confidence interval for the population mean mu. Okay, now, first blush, we might notice, if you're up to speed on things, the Z value, corresponding Z value for a 95% interval is 1.96. This is bigger. This is bigger. More uncertainty, bigger t, larger margin of error, wider interval, accounting for this extra variability that is necessitated by the use of using the sample standard deviation in place of the population standard deviation. So let's compare it for a few, just to compare what's happening here. Remember again that that t distribution is tending towards the standard normal as the degrees of freedom increase. So it's going to get closer and closer. And when we start off small here with a sample size of 2 and 1 degree of freedom, well, we get this really big t-value, right? 1 degree of freedom is kind of weird stuff happening with the t. But so you get a lot of area out in the tails. And we have to go really far out to capture the appropriate area. So you get this t-value that's way bigger than 1.96. But as your degrees of freedom increase, that's getting bigger and bigger, smaller and smaller, and getting closer and closer to the 1.96, which is the infinite degrees of freedom case, which is the standard normal distribution. So our t, as the degrees of freedom increase, the t distribution is getting closer and closer to the standard normal distribution. And then, of course, t.05 is going to get closer and closer to this 1.96, which is the z.025, right? t.025 is getting closer and closer to z.025, which is this 1.96. Okay, so the t, if we use let's say if we use the z in places we should be using a t, if we use the z where we should be using a t, the value we use in the formula is going to be too small, and our margin of error is going to be too small, and we're going to be having too narrow an interval. We're going to be lying. We're going to be telling falsehoods. So we need to properly incorporate things, and so we need to use the t-value. Now, old school, I'm about to say an old school way, and I'm bringing it up in the context that I want you to forget it. Okay? Because if I don't say anything, then you'll watch on whatever your tutors or whoever you're listening to that tells you all sorts of weird stuff. And old school, people would say, if we have a sample size of at least 30, it's all good and it's close enough. No. If it's a t, we use a t. If it's a t, we use a t. And there's quite a bit of difference here, right? I mean, the 30 degrees of freedom, 1.96 is not the same thing as 2.042. If it's a t, we use a t. What's the difference between a t and a standard normal? Well, what I laid out, not some other stuff. For sampling from a normally distributed population, and we have that quantity, right? We're putting in our sample standard deviation and not the population standard deviation, then we have ourselves a t, and that's just the reality. So if you're trying to publish a paper and you say, oh, my sample size is 60, I'm going to put a z in there, you're going to look foolish, okay? It's a t in that spot. All right, let's do a real example. So here's a real example for you. I find this question rather interesting, and it has been coming up a lot recently with people and inflation, etc. People taking more notice of certain things, and I have a bit of casual expertise, I might say, in this thing because I have measured many food items over the years. I have bought lots of stuff and measured because I found it interesting. How much is actually in there? Okay, so a few years ago, I got these bags of cereal. I am a cereal lover, so I do eat a lot of cereal sometimes, and I got a good sale on these Sally's Sweet Wheat bundles. And their nominal weight, they said in the bag, was 368 grams. I liked them. They were really cheap. I said, what the heck? And I bought 15 bags of these. And said, I'm going to measure these. I ate them through time. I got my little scale. Didn't put the bag. I got the weight of the cereal, right? Without the bag, just the cereal weight in there. Okay, here's what we get for those 15 bags in grams. I get these. Again, nominal weight of 368. They're saying 368 grams in there. How much is actually in there? It's a very legitimate question, I think, I would like to know. So this is what I got. So just for these 15 bags, I have a mean, my X bar, because it's a sample mean, because I'm talking about these 15 bags, which is a sample, right? That's my X bar, 374.47 grams. And this is a sample standard deviation as well. We have to be able to determine that. I'm just saying the 15 bags had a standard deviation of this. That means that's sample. That's the sample standard deviation. And so that's our sample standard deviation. So overall, just sort of casually here, they're saying 368. I'm getting 374 grams. Now that's an estimate here of the true mean weight, say, but I might want to come up with a confidence interval. And we'll talk about aspects of this, like what is the population mean in this context in a minute or two. But overall, we've got a point estimate from the 15 bags. Let's say we want to run this through and get a confidence interval. Okay, first, plot it out, have a look. We plot it out and have a look. The method assumes that we've got a simple random sample from our population, and it also assumes a normally distributed population. And so these visuals are checking out the normal distribution part of things. There's only 15 observations here. So as we'll see, we feel a little more comfortable about it when we have larger sample sizes, but there's nothing wrong with doing this procedure with 15 observations. Totally legit. Overall, it looks like this from if we look at the box plot, right? Look, the values we're getting are greater than the nominal weight by the looks of things. Have one bit of an outlier here, but it's not too extreme. Nothing too extreme there. Overall, looks pretty symmetric. Maybe you have that one fairly large value, that kind of thing. And if we do a normal quantile plot, and the raison d'etre for a normal quantile plot is to investigate whether our sample data is roughly normally distributed. And we can do that with other plots like histograms and box plots, but normal quantile plots are the best for that. That's a reason for being. Their design is enabling us to look at that as best as possible. So overall, I think this is okay. These are, a couple of big ones here. Maybe you could think maybe a bit of an outlier, but nothing too extreme. And in these normal quantile plots, if you remember, when we're sampling from a normally distributed population, we're going to expect these things to roughly fall on a line. That's what's going on with them. That's the gist of it. If our population's normally distributed, then we're going to think typically our sample data points are going to fall roughly on a line. So this is what we're investigating. These are looking pretty good. Got a couple of sort of bigger ones up here. I don't think it's a big deal. I think we're okay. Right? I mean, reasonable to think you're mildly troubled by the outlier there, but they're not extreme. I think it's fine. So we'll talk about the sampling too. So the gist of it, how I got these, it's pretty much, I think, reasonable to think it was a random sample from the bags at that store. I think it was that. I was just sort of haphazardly grabbing them, but I don't think there was any systematic issues there. We could talk about subtle ones, but think of it as a random sample from the ones on sale at that store that day would be pretty reasonable. So I think we can go ahead and do this. And the overall notion, if it's normally distributed, we're using our sample data here, and we're going to go through and crank through some of these. We had 15 observations, right? So n is 15. Our degrees of freedom, right? I'll call it DF here for degrees of freedom, right? I could call that new and just saying our degrees of freedom for our T are n minus 1, and so we've got 14 degrees of freedom here, right? So 14 degrees of freedom, and when we want our appropriate T value, saying we're doing 95% interval, so we're putting 0.95 in the middle, 0.025 over here, half the area on one side, half the area on the other, and this is the value we want. We want the T value that's our T 0.025 for a T distribution with 14 degrees of freedom. 0.025 to the right, 0.975 to the left. If we put that into R, we get 2.145. Okay, so 374.47 plus and minus our margin of error. And if we go through and we do it, well, you can do this in software terms. So that's how we do the calculations, right? So this is our 95% margin of error. And I'll tell you what, before we start interpreting this, let's go see how we'd actually do this. So I'm showing this is what would happen if we're hand cranking this sort of stuff with the use of software to get the value. But R will do this for us, right? Because statistical software knows we want confidence intervals. So it'll help us get these things. And this is how we do it in R. So Sally's weights contains those 15 weights. I'm using something called t-test. We are not yet doing a test. We will do a test. Testing and t-tests are going to be important for us. But this is all complete junk. Well, it's actually overall complete junk. It's definitely junk for us now. We just do not look at this. I am using t.test because we're going to need it later, but it also outputs the confidence interval. We have our confidence interval, which is the same as what we got up here, right? That's just saying it's just from here, what we calculated, doing this type of stuff we got there. This is the same. And so we get this confidence interval, a 95% confidence interval from mu. So 372.9 grams to 376.0. I'll just put it to one decimal place. We can be 95% sure that, first of all, 95% confident that the population mean mu lies in that interval. That's what we went with before, but that's true. But we need to translate that to the practical problem at hand, the practical points of interest here. So what's going on? What is mu? So what is mu? So we are trying to estimate the true mean weight of cereal bags of this type. And we've come up with this 95% confidence interval for that. And so mu is the true mean weight of cereal bags of this type. So we could say that we are 95% confident that the true mean weight of cereal bags of this type lies between 372.9 grams and 376.0 grams. That's the deal. Now, there's something hidden a little in there, okay? And this is real world stuff, right? Real world stuff, which is often the case. What do we mean by of this type? Cereal bags of this type. I was a little vague there. Technically speaking, our conclusions are going to relate to the population that we sampled from. So here, really, I sampled from the bags on store, randomly sampled from the bags on sale at that store that day. That would be sort of specifically what we're drawing a conclusion about. But of course, this gives information. If we casually go, and we often do this in statistics, we've got sort of the specific thing we're saying, but just sort of casually, we're using our senses, we're using some common sense, we're thinking, okay, well, it is likely giving us some information a little bit beyond there. That perhaps not just that store, might be from bags produced at the production facility that produced those, or those kind of things. Gets a little awkward because, of course, these things change through time, etc., etc. And you might think, oh, this is complicated and confusing. Yeah, that's life, okay? This is exactly how it works. So this is the nature of it. Specifically, if we restrict ourselves, just that population from which we sampled, it's fairly straightforward. We're 95% confident that the true mean weight of cereal bags of this type lies in this interval. It's just a question of how far out can we go here? Are we talking about just that store? Are we talking about from that lot? Are we talking about that production facility? Obviously, if we go too far and just say of all cereal bags, that's just dopey, right? So it's a question of, the farther out we go, it starts getting sketchier and sketchier. And there's nothing mathematical that allows us to go out. We can only really talk about that population from which we sampled. But we can use our common sense and our brains and just think about, well, maybe this likely is giving us some information about these types of bags of cereal in a little bit more general setting. And just as a casual aside here, it's all the rage to be talking about how much you got shorted buying your macaroni at Loblaws these days, but this is typically the case for produced food. I am not someone who comes to the defense of businesses all the time and all of their practices, but on this one, when you're buying things that have a stated certain weight, the companies, from everything that I've seen, and I've seen quite a bit, are pretty good at giving you a little bit more. They don't want to face complaints about being shorted. It happens sometimes. It happens systematically sometimes. Heinz got dinged with a big fine a number of years ago for shorting people on their ketchup, right? These kind of things. And no offense to Heinz, they did face a fine from that, I believe, and I don't think they were doing it intentionally. It's just one of those things that just happened along the way. But all of that is rare. These companies tend to put in a little bit more than they're saying. They don't want to have to deal with the complaints. It's not to say we shouldn't be vigilant. Check it out, but they're usually pretty good. Okay. So what did we do? What did we do with all this? So just some assumptions of our one sample T procedure. Why does this work? When does this work? Well, the assumptions here, as I've been talking about with the interpretation, we have a simple random sample from a normally distributed population. So this is the fundamental to this, that we've got a simple random sample from a normally distributed population. The sampling design is hugely important always. If we have very biased sampling design, then our reported results at the end might be very, very misleading. Normal distribution is always something that's kicking around, but it's most important for small sample sizes. For large sample sizes, that central limit theorem starts kicking in and really helps us out. Maybe not perfectly, but it helps us out. Where if we have larger sample sizes, if the population is a little bit right skewed or something, starts to be not really big a deal if we get large enough sample size. So let's just sort of give some kind of ideas along these lines. So if the population's not normally distributed, what happens? What are you talking about? That's an assumption. Just assumed it. It's not true. So what? Well, the so what we're going to look at, right? So what happens if our population's not normally distributed? Well, first of all, some terminology. Statistical procedure is called robust to violations of an assumption if it still works pretty well. That assumption's violated. And the T procedures, these are very good news. T procedures that we used here are robust to many types of violations of the normality assumption. A little bit of skewness, this way, that way, right? Just various things, doesn't quite look normal, not quite mound shaped, right? A little bimodal or something. Just the T distribution, the T procedure that we used here works quite well still. So still for some violations of the normality assumption, these T procedures work really quite well. And so it's one of the reasons why this T is very, very important procedure, and these methods we're talking about are important, is, okay, we've got this strict assumption of a normally distributed population that we're sampling from, but, a little non-normal, no big deal, still works pretty well. It's not true of all statistical procedures. Some are very sensitive to violations of these assumptions, but these T procedures that we're talking about today work pretty well and for many violations. Okay. One thing to keep in mind, I'm going to give a little guideline about some sample sizes here and that type of stuff. We shouldn't just forget about violations of the normality assumption if just because we have a large sample size. If we have a large sample size, the procedure might be working pretty well. Maybe we've got some right skewness. And we say, no big deal. We got a few hundred observations. This will still work well. Sure, maybe we're still working well because we've got a large enough sample size. But in most situations, we'd like to take care of that non-normality. If we have some skewness, we'd like to take care of it and get something a little bit more normal. We'll talk about transformations in a second. So there may be better methods such as transforming the data using a distribution-free procedure. Even if we do have, if the T is working reasonably well, we should investigate that normality assumption, see what our data looks like. Okay. Very rough guideline, and I mean this as very, very rough guideline. Very, 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 very rough guideline. Very rough guideline. Okay, once we start getting reasonable sample sizes, 40, 60, 120, these kind of things, your T procedures that we've been talking about are going to work pretty well. Going to work pretty well, right? They're just, pretty well in most practical settings. Still can be thrown off by wicked strong skewness, massive outliers, these kind of things. Skewness, T's don't love the skewness and the outliers. These kind of things can really get thrown off. But if our data isn't really all that weird, there isn't really strong skewness, it's looking okay. Once we start getting up to 40 and this kind of stuff, we're in pretty good shape as far as the violations of the normality assumption not having a big impact, as long as the violation's not too severe. A little bit smaller, and there's a big difference between 15 and 40, but just sort of, again, rough guideline. You're still okay. You're still okay. But when we start getting some these outliers and strong skewness, it can throw us off. It can be just an inappropriate procedure to use. If we have 18 observations and we have some strong skewness, it's pretty sketchy to be using the T procedure, and we're going to be getting misleading results a lot. When we get smaller still, well, we're going to only really want to use these T procedures when we're feeling pretty good about the normality assumption, and it just starts to be a little bit sketchy to just jumping to the T distribution or T procedures that are based on the T distribution when we have a pretty small sample size. So rough guideline again, rough guideline here. So in here though, tied in with that, what do we do? Is it, okay, sometimes we use these, sometimes we don't. What do we do? If we feel that the assumptions are not justified, three main things. Maybe we have an inference procedure based on a different parametric distribution that our data does seem to fit. Maybe our data seems to fit like it comes from an exponential distribution or a Weibull distribution or any one of the other distributions that actually fits our data and has a procedure for that particular distribution. We have some of those. Maybe we're lucky. Maybe it's not normal, but hey, we can do similar things for other distributions. This is going to be a big one for us, though. Use the t-procedures on a transformation of the data. So under things like right skewness, we have right skewness of times to events or something like that. And there's right skewness, say. We have right skewness like that. Sometimes if we take the log of the times or the log of the data values, that just maps us over to something that does look pretty normal. So sometimes under some right skewness, we take a log or take the square root of the data values, that sort of thing. Sometimes that just takes care of it. Sometimes almost magical, right? Not always, but sometimes almost magical. It just turns, hey, that's pretty darn normal after the transformation. And then what? Well, we're in great shape. Just use the t-procedure. All we did was take the log of our data values. It looks normal. Everything looks nice. We can go ahead and use the t. So it opens up a whole other world. Even when we're not sampling from a normally distributed population, maybe there's a transformation that makes our data have roughly a normal distribution, and then we can just use the t anyway. That's pretty easy. Just transform the data values, move on with your life doing the t like we know how to do. Or distribution-free procedure, non-parametric procedure. These procedures do not assume any particular distribution of the data, not a normal distribution or an exponential distribution or Weibull or a gamma, whatever other distributions we might want to talk about. They are more general and useful in a wide variety of settings. And so you might say, hey, wait a minute, you've got some secret methods that don't have this assumption. Why the heck are we using a method that does have the assumption? Why we have this extra thing? I don't want to assume normality. You're telling me there's other things we could do that do assume that don't assume normality. Why are you teaching me these? These t procedures are the best possible procedures when we are sampling from a normally distributed population. They work better than anything else. Okay? These are optimal in that setting. The t procedure is optimal in that setting. When our assumptions are satisfied, you cannot do better than a t procedure for the intervals or the t-tests that we'll do later. So when your assumptions are violated, maybe they don't work so well. But for these distribution-free procedures, if you're being street smart about this, they're useful in a wider variety of places. So then there's going to be spots where they're not that useful, right? Or not as good as other procedures. So these distribution-free procedures are useful in a wide variety of spots. They just don't have the same restrictive assumptions. Work really well. Very common things. We use them. We love them. We do them all the time. Non-parametric procedures. They're great. They're a wonderful thing to have in our arsenal. We do these things in statistics a lot. They're great. But if we are sampling from a normally distributed population, the t can't be beat. So things like we would end up with a narrower confidence interval using the t than if we tried to use one of these non-parametric procedures. When we're sampling from a normally distributed population, our t procedure is going to be best. But when it's not normal, maybe that's, depending on the specifics of the situation, it might be messing us up to the point where we'd be better off using a distribution-free procedure. Or, the first thing, I think typically the first thing statisticians think of is doing that transformation. Because maybe the transformation will work out nicely. And if it does, doesn't always, but if it does, we just use the t procedure and we're good to go. Anyway, more details at another time.